Hello, this is question 7 from the Step 2 paper from 2023. 6 parts to this question, complex numbers, okie dokie. So complex numbers Z and W have real and imaginary parts given by Z is A plus IB and W is C plus ID. Prove that the modulus of ZW is equal to mod Z mod W. Okay, right, so this should be fine, shouldn't it? So let's work out what ZW is first of all. So ZW is going to be what we're getting, AC minus BD plus, for imaginary, we got AD plus BC. Okay, so that's our ZW. So let's do the modulus of that, which is going to be the square root of AC minus BD squared plus AD plus BC squared. Oops, a bit of a wonky square root, but it's just about okay. So what we're going to get, an ABCD, they're going to cancel the ABCD terms from those. So we've got A squared C squared plus B squared D squared plus A squared D squared plus B squared C squared. And then square root all of that. Okay, and then we've got mod Z is A squared plus B squared square rooted. W is then, what was it, C's and D's, C squared plus D squared. So I just need to multiply these together. So multiply those is going to be the square root of A squared plus B squared times C squared plus D squared, which looks as though we're fine. So A squared C squared plus B squared D squared plus A squared D squared plus B squared C squared. Okay, which is exactly what we want. Okay, so that's part 1. Part 2, by considering complex numbers 2 plus I and 10 plus 11I, find positive integers h and k such that h squared plus k squared is 5 times 221. Okay, let's go over this side. This is clearly following on from what we've just done here. So let's deal with that, get that magnitude there. So that's going to be root 5, because we've got 4 plus 1. Then we've got 10 plus 11i. So that's going to be 221. So there are our two numbers that we got here. So square root that. So if I multiply these two things together, because that's what we're doing in the previous example, well, that one, the ZW bit. So 10 plus 11i. So that's going to be 20 minus 11, and then 22 plus 10, so 32i. So that means then that we've got, so multiplied together, the modulus of that, so 9 squared plus 32 squared is going to be equal to if I take I could have the square root, but I don't need the square roots on. I can get rid of square roots on all of these. That's going to be a 5 times 221. If I was actually doing the modulus on all of these things, of course I'd have square roots, but let's just square everything. So I think that's what I want, isn't it? So I've got 9 and 32. So h equals 9, k equals 32. Or the other way around, whatever way we want to do it. Okay, that was a quick one. Right, let's see if I can get 3 on this bit. I've got a bit of space here. Find positive integers m and n such that m squared plus n squared is 8,045, I should say. Right, so we need to split that into two numbers that are multiplied together, and clearly 5 is going to be a good option, isn't it? So we can say 8045. So I want to divide this by 5. So that's going to be 1600, will get us up to 8,000, and then another 9. So 1609. Okay, so this is, and again, just thinking back of how we've done this. So we got that 5 by having that, and we got that 221 by having that. So we need to have 1 thing, well, let's say 2 squared plus 1 squared. We want to add up squares. So that would be 40 squared plus 3 squared. Okay, so we now need to do 2 plus I times 40 plus 3i, which is going to be 80 minus 3, so 77. And then we've got 40 plus 6. Okay, so that means we need to square those numbers. So 8045 is going to be 77 squared plus 46 squared. Now, this is a nice question so far, and they've been quite straightforward parts. Right, now we're given 102 squared plus 201 squared is 50805. Okay. Find positive integers p and q such that p squared plus q squared, well, that's a bit easy, isn't it? I mean, that's not even following on from what we've just done. Because if we've got 102 squared plus 201 squared is 50805, then if we multiply both sides by 6 squared, this is a bit of a weird interlude. This, I'm assuming this is going to lead us on to something that we're doing in the rest of the question. So I just need to multiply these things by 6. I'm going to have 612 squared plus 1206 squared is equal to 36 times 50805. So P is 612, Q is 1206. Okay, so it's done that one. This is flying along. So part 5, find 3 distinct pairs of positive integers r and s such that r squared plus s squared is 25 times that thing. Right, so we've got a number of things we need to do here then, haven't we? And we've got our 5 squared there. So we've got r squared plus s squared is equal to 5 squared times all of this thing. Now, going back to the previous part, we need this bit. So ignore the 5 squared. Get 2 numbers that are going to square and add up to this thing. So what are we going to have for that then? So this is how many? 1, 2, 3, 4, 5, 6. It's got an 82 at the end, which is making me think, yeah, that'd be a symmetrical number. So this thing, we've got 1002,082. That is 1002,001 plus 81. So that's going to be 1001 squared plus 9 squared. It's a useful pattern to spot on these. If you're just adding 1 onto a power of 10, then you get this pattern. Like when we do 11 squared, you're getting 121. Every time you put another 0 in there, you're putting zeros in the gaps between the 1s and the 2s. So we got that, and I've forgotten what I'm doing. So that's given me, that's given me the equivalent of that bit. So that's good. And now I need to multiply by 5 squared on these things. Okay, so that's going to be okay. So I'm going to have, actually, that's only giving me 1 pair though, isn't it? That's only giving me 1 pair out of all of this, and I want to get 3 pairs out of all of this. Anyway, I might as well bank that 1. So I've got that, what is it, 5005 squared plus 45 squared is equal to 5 squared times 1002,082. So that is 1 pair then of 5005 and 45 for our R and S. We've got R is less than S, so R and S. Okay, so how am I going to get another pair on all of this then? So what we're saying, let's just make this a bit clearer what I've actually done. So we're coming back to this at the very start in the first part of the question. I just want to make sure I'm getting this right. So I've got that mod Z mod W. So we could say that, which way around do I want to do this? So if I've got say one of them was 1001 plus 9i. So if I got the mod of that, that we've already said comes out at this. And then I need to multiply that by something which has got a 25. Oh no, actually that squared comes out as being that. So I need to multiply this by something which has got a 25 for the square of the magnitude. Yeah, that's what I need in order to have this. So if I had something else, well, 3, 4, 5 works, doesn't it? So if I had 3 plus 4i squared would be 25. So if I multiply these together, I'm then doing this, and that ZW would come out. Right, so this is like saying that's my Z, that's my W. Let's get ZW, and then we'll be okay. So, well, they're not Z and W, that's the magnitude of those. So ZW is going to be 1001 plus 9i times 3 plus 4i. I suppose I could have done 4 plus 3i. That's probably how I'm going to get two separate solutions for this. So let's say or equals 1001 plus 9i times 4 plus 3i. Okay, so what's this then? So that is 3003 minus 36. And then for i's, I've got 4004 plus 27. So 4031 I. Okay. And then, well, this is going to be 33 off of there. So 2967 plus 4031 I. So they should be my two numbers then. So that's saying that I've now got R is a small one, 2967. S equals 4031. Then for this one, I've got 4004 minus 27. And then for i's, I've got 36. All right. Yeah, 36 plus 3003. So 3039. Okay. So that is, take 23 off of there. So that's just going to be 3977 plus 3039i. So I could have R is 3039 and S is 3977. Okay, that was a bit more involved, but again, it wasn't that bad. We're just following this same thing that we had in part one. You know, it's been we've done the same thing in every part of the question so far. So that's all right. We've got one bit to go. You are given that equal, okay, we've got the same sort of pattern here. We've added a 36 on the end. Find positive integers t and u such that tu squared plus t squared plus u squared is 9193. Okay, so how am I going to go about doing this then? Well, I'm going to want to split it up much in the way that I've split things up before. So if I've got 109 times 9193 is equal to this. I'm doing all this stuff as the sum of squares. So I've got 10 squared plus 3 squared. So that's going to be one magnitude that I can put in. Then I've got t squared plus u squared, because that's what we're trying to work out, given us in the question. And that is going to be equal to 1001 squared plus 6 squared. So it's all fitting into just being these magnitudes of these complex numbers. So that is going to be 10 plus 3i squared, and then I need to multiply that by t plus ui squared, which is going to be 1001 plus 6i squared, magnitudes of all of those. So I can just equate real and imaginary now on all of this, and it should all be okay. Right, so how's this going to work then? Because I can come back to doing this. You know, I've got a Z and a W here essentially on the left hand side. So if that's my Z and that's my W, now do ZW in the mod of that. So my ZW is going to end up being 10t minus 3u. That's the real part. And then the imaginary part, I'm going to have 3t plus 10u I. So I now equate these things to each other and say, right, well, 10t minus 3u has got to be equal to 1001. And that 3t plus 10u has got to be equal to 6. Okay. And what does that leave? That leaves me with, well, I suppose I've got to multiply. There's no like simple way of doing this. Well, look at it with 10s and 3s. So let's go 30t minus 9u is 3003. So 30t plus 100u is equal to 60. So it subtracts the, well, bottom one from the top one. You get something slightly awkward either way. So minus 109u is going to be 2943. Okay. So u is going to be minus, God, this is a mess, isn't it? So if you've got two lots of 109, I'm trying to divide it 109 into 294, just doing a bit of bus stop here. So that's going to be an 18, so I'd have 76. So 763 is going to be 7 times. So I've got minus 27 then for u, which means that t is going to be equal to, so what have I got here? Let's go back to this one. 3t is 6 plus 270. So 276 divided by 3. Is that right? Yeah. So that's going to be 92. Okay. So is that all we want? Positive integers t and u such that t squared plus u squared is that. So yeah, that should come out all right. So I've got that 9193 is equal to 92 squared plus 27 squared, which seems plausible, doesn't it? Because if we add 100 squared, then I'd be getting 4 zeros, which is, so it's a bit less than that add on a 27 squared. So it seems in the right ballpark. That was a really nice question. It was quite a quick one, but I liked how we were just doing the same thing, variants on the same theme all the way down. It was really reusing over and over again this thing that we proved in part 1, and then just reapplying it. Plus it's got lots of nice number manipulation, which always makes things a little bit easier. So yeah, that was a very, very nice question.